going to look at quadratic and rational inequalities. These can get a little complicated, so it's important when you're working these problems to lay your paper out neatly, try to make it easy to follow the process because it's not necessarily a straightforward process. It's going back and forth to work the problem out. There's two approaches discussed in the textbook. One's called the sign diagram, the other the critical value. I find the critical value more useful in different situations, and to me it's a little bit more straightforward. You can use a sign diagram if you think that works better for you. Okay, what we're going to start with is looking at a quadratic inequality. X squared plus 5x subtract 6 is less than 0. And this is one that factors nicely to x plus 6, x subtract 1 is less than 0. Now if it was simply equal 0, we could solve this and say x equals negative 6 and x equals 1. But this is an inequality. We want to know when the value of the function is less than 0. So something to think about. At negative 6, this part of the inequality, the x plus 6, this factor, switches from being a positive value to a negative value. And at x equal 1, the other factor, x subtract 1, is switching from positive to negative. And then those two factors are multiplied together. So the way this works, if both of these are positive, a positive times a positive would be positive, and that would not satisfy the inequality. But if one of these is positive and one of these is negative, then this would be true. This product would then be less than 0. That's kind of how the sign diagram approach works. But again, what I think, for me, what works a little better is the critical value process. So what we're going to do is look at each factor and find the two values for when the factors are 0, negative 6 and 1. We're going to call those critical values. And then we can take the two critical values, the negative 6 and the 1, and that divides the number line into three different areas. The values below negative 6, the values between negative 6 and 1, and the values greater than 1. And then we're going to arbitrarily pick three test values, one out of each of these three regions. This is where it seems a little weird because there's lots of values we could pick to be the test value. So negative 7 is one we picked for this area. We could have easily picked negative 10. And then 0 is an arbitrary value in this range between negative 6 and 1. And then 2 is an arbitrary value in the here greater than 1. And we could have picked, 2, 3, 4, 5, 6, any nice number that's greater than 1. And then we take each of these three test values, try them in the original inequality, and see whether or not they satisfy the original inequality. So our original inequality was x squared plus 5x subtract 6 is less than 0. If we let x equal negative 7, substitute that into the expression, and then what we're looking for is, do we have a true statement or a false statement? And what we've got here is that 14 subtract 6 is 8, 8 less than 0, that's false. So we do not want this region in our test interval. Now taking 0, plugging it into our inequality, simplifying it, 0 subtract 6 is negative 6, negative 6 is less than 0, so this is true, so we do want this region. And then taking our third value here, our third test value, substituting it in, 14 subtract 6 is 8 less than 0, that's not true, so we don't want this region. So the region we want are the values between negative 6 and 1. And because we're actually looking for the values to be strictly less than 0, we don't want to include the actual test values, the actual critical values, the endpoints of the interval, the negative 6 and the 1, because at negative 6 and at 1, that makes the function actually equal 0, and we want to be strictly less than 0. So our solution is the interval from negative 6 to 1, not including the negative 6 and 1. Or you can read it as 6 is less than x is less than 1. So in general, to solve a polynomial inequality, set each side equal to 0, find the zeros of the polynomial, these form the critical values, that divide the number to test intervals, pick an arbitrary test value in each test interval, but you can't use the critical values, and evaluate the polynomial to see if it satisfies that inequality. Here's another example. This one's a cubic. X cubed subtract 5x squared subtract 6x is greater than 0. And easy to factor an x out and then factor the remaining quadratic. And so we have three different factors, and we've got three different critical values, 0, 6, and negative 1. And with those three critical values, that divides our region into 4 different test regions, so we need 4 different test values, one from each of these. And again, substituting back into the original inequality, when we use x equals -2, we get -16 is greater than 0, which is false. Plugging in -1/2, can't read that, I think it's 13/8 is greater than 0, which is true. Using +1, substituting into our polynomial, we get -10 is greater than 0, which is false. And then using 8, we get 144 greater than 0, which is true. So we want these values here between -1 and 0, and these values here from 6 to infinity for our solution. Okay, now to solve a rational inequality, what we're going to do is set one side to 0, and I left a step out here. And then we want to write the expression with a common denominator. And we find the zeros of the numerator and the denominator. So we're going to set the numerator equal to 0 and solve, set the denominator equal to 0 and solve to get our critical values. Where the numerator is equal to 0 is where it's going to change from positive to negative. And where the denominator is 0, it's where the function is going to be undefined. So both of those together are going to form our critical values. And then again, we'll pick a test value in each test interval and evaluate to see if it satisfies the inequality. Okay, so we've got 2x plus 1 over x subtract 3 is less than or equal to 0. So we've already got the 0, and we've already got a single denominator. So to find the critical values, we let the numerator equal 0 and get one critical value, and let the denominator equal 0 and get another critical value. So -1/2 and 3 are our critical values. So taking the 2 critical values, we've got our 3 regions. We've picked an arbitrary number in each of the 3 regions. Okay, so testing with the -1, substituted in, we get 1/4 is less than or equal to 0, which is false. Using the 0, we get a statement that is true. -1/3 is less than or equal to 0. And then using the 4, in our third test region, we get a false statement. So we don't want that region either. So in this particular case, we want the numbers between -1/2 and 3. And now we got to think carefully about the endpoints. We never want to use the 3, because looking back at our original problem, if x is 3, we get a 0 in the denominator, and that's undefined. So that definitely does not satisfy our inequality. Because we're less than or equal to 0 in this particular inequality, we do want to include the -1/2 in our final solution, because that gives us a 0 in the numerator, and 0 over, let's see, would this be about -4.5 is 0, and because it's less than or equal to 0, we do want to include that value. So we're going to have the -1/2 to 3, including the -1/2, but excluding the 3, because at 3 the function's undefined. Okay, now this particular example is a little more complicated because it's not set equal to 0. So if we bring the 1 over to the left-hand side, we then need to get a common denominator, combine the 2 expressions, simplify, and then we get to where we can start solving the problem like the previous one. So again, we're going to set the numerator to 0 and the denominator to 0 to get the critical values. So that's up over here. So 2 critical values are -8 and -3/2. That gives us 3 different test intervals. Again, it's arbitrary how we're picking these test values. We just an arbitrary number in each of these regions. So I picked -10. -9 would have been 5. Fine also. So would -268. Any number less than -8. Any number between -8 and -1/2, and any number larger than -1.5. So checking each of those test values, simplifying, and I went all the way back to the original inequality. I've got a false, a true, and a false, so I want the area in between. And again, I'm going to include the -8, because that makes the statement actually equal to 0, the numerator equal to 0. And I'm going to exclude the -3/2 because that makes the denominator 0. We can never divide by 0.